So far in the modules, earlier modules we have talked about optical transmitters. In this module and in the next module we will discuss optical receivers, and then we will come back to transmitter, physics behind transmitters and physics behind receivers. So at this point we are not really interested in how to implement a receiver, what physical device actually is used to convert the optical signal into electrical signal, except that I can mention that this is a photodiode. Okay. We are not looking at the physics behind photodiode or the circuits that would be implementing the optical receiver. This is the configuration idea. Again, going back to the approach that we have taken in this course, we will first describe by mathematical expressions what is the basic idea behind this block, optical receiver block, and then come back and discuss the physics behind it, at a later stage. So having said that, optical receivers are used to convert optical signals into electrical signals. Okay. Optical signals are the ones which are generated by the optical transmitter. So you take the continuous wave laser diode, you can pulse shape it or you can shape that signal and then modulate that optical pulses in order to generate an optical waveform. So you will be getting modulated optical waveform after transmission through the fiber and maybe other components, WDM components, and eventually arrives at the receiver input. Okay. So at the receiver input, the signal will usually be very small, so you will have to amplify the signal first, and after amplifying you will have to pass it through a filter in order to remove the extraneous noise that is not required for us to process. This way now your optical waveform is ready for conversion to electrical signal. You might ask, why should I convert this into electrical signal? The answer is very clear. The information originally was in the electrical domain and I need to extract that electrical information from the optical signal. So I need to convert optical to electrical signal. What form of electrical signal? If I use a photodiode, then this conversion is usually in the form of a photocurrent. So it will produce a current, a photodiode will produce a current. Okay. So this is the photodiode for us, this is just a block diagram at this point. You send in an optical signal, say E of t, okay, where E stands for the electric field, and what you get here would be a signal, electrical signal, which is proportional to E of t square, mod E of t square. E of t could be a complex waveform, the phasor waveform, and you will be generating the signal or the photocurrent which is time varying, but it would be magnitude of E of t square. For example, let us consider a continuous wave. So if my electric field, incoming electric field is a simple continuous wave signal from the laser diode, this could be equivalent of having a laser diode and then connecting a photodiode. Okay. So this would be the simple situation in which I am taking a laser diode, giving it a certain current, not modulating anything, just giving it a current and then putting a photodetector to detect the signal. What do I see? This E of t, what I get can be represented as square root of Ps e to the power j omega st. You can also have some phase information sitting inside. Okay. This phase information, if you have not actually modulated the signal, will simply correspond to some phase offset or some random phase which is associated with the laser. Okay. So when you look at that into the photodetector, what you see is the photocurrent, which is actually the average of E of t mod square. I forgot to put in the average. What you get here is the average value of E of t mod square. But what is the average value in this particular example? In this case, I know that E of t is given by square root of Ps e to the power j omega st plus theta of t. So if I take the magnitude square here, I get Ps and then average this one out, the fast varying time component drops out and I simply get Ps, okay, which would be the power with which the laser is supplying the signal. Okay. Forget about this half or other factors, there would be a half corresponding to the cosine signals, don't worry about those factors. What is important to note is that a photodetector or a photodiode, which is acting as a photodetector, will generate an electrical signal which gives you the photocurrent which is given by average value of E of t mod square. Now this is very crucial for you to note that we have seen some modulation techniques which only alter the amplitude of the optical signal. This is the amplitude shift keying that we discussed in earlier modules. We have also seen in earlier modules those modulation techniques which will alter not only the amplitude, but both amplitude as well as phase. We have also seen those which will alter only phase. So if the information is residing in the phase theta of t, and I have used a photodetector to detect my signal, optical signal, and convert that into electrical signal, I have clearly lost all the information about the phase. I have totally lost it, right. So there has to be a way in which I have to extract information which is located in the phase of the optical signal, but still use a photodiode. Okay. So we will see what kind of a receiver circuit is required in order to do that one. We also discussed one modulation technique called as differential QPSK or differential BPSK. This differential modulation was in the form of encoding phase as the, or encoding the symbols as the phase difference between present and previous symbols, right. So the next symbol that you are going to obtain will be a function of present and the previous symbols. So the phase difference between those two was actually being transmitted. So in a similar way, if I want to extract the phase difference between two time slots, I have to convert the phase difference between two time slots into intensity value. So again we will see what kind of an optical receiver is required for that. So although this is titled as optical receivers, we are really looking at the detection mechanisms. A full receiver will consist of a biasing circuit, it will also consist of some low noise amplifier and a main amplifier. A low noise amplifier is also sometimes called as a preamplifier, and then you will have a main amplifier, some additional filtering circuits, some detection and synchronization and timing circuits. All these circuits essentially form a part of optical receiver. We are of course only going to concentrate on one particular component known as the photodetector, and what are the receiver topologies, what are the photodetection topologies that will enable us to extract information from phase of the optical carrier or extract information about the phase transition. Okay. Whatever we have done by putting up a laser and a photodetector is known as direct detection. Even today for 10 Gbps to 40 Gbps data rate systems, direct detection, laser intensity modulation and direct detection is the simplest, hardware efficient and most widely understood and implementable detection receiver topology. All that you have to do in the direct detection is you have to simply put a photo detector. The optical signal comes and falls on the photo detector and you simply generate the photo current. Okay. This photo current can flow through a certain resistor generating the voltage, or you can, in the more common scenario, you can actually convert this photo current into a voltage by putting a current to voltage converter in this fashion. This one is a simple receiver module, whereas this is a simple module, whereas this is called as trans impedance amplifier. Okay. This structure is quite widely used for photo detection purposes. What does this detection mechanism consist of? It simply consists of a appropriately biased photo detector followed by a way to convert current into voltage. You can do that by simply putting up a big resistor, or you can put up that same resistor but couple it through this op amp in order to form the trans impedance amplifier circuit. Okay. If my intensity is changing this way, optical intensity, and it is changing very slowly, this is not the carrier optical that is changing. Please remember this. This is not the optical carrier, this is the modulated laser light. Okay. This is the modulated optical or intensity modulated. Okay. This is the intensity modulated optical signal as a function of time. Then if this modulation is quite slow, right. So if you remember it, there is actually a very high speed carrier sitting here, right. So there is a carrier here. So what you are actually looking at is the intensity that is getting modulated, right. So this is the modulated waveform, a slowly varying envelope. If you put this one through the direct detection photo receiver or a photo detector, what you will see is a photo current which will essentially vary in the same manner as the input. If I am using amplitude shift keying or equivalently an on off keying, my optical waveform could look like this, right. So, I have wherever I have a pulse, there would be some signal, and when there is no pulse, the optical power could be sitting at P0. So, this would be the power levels through which this is switching as a function of time. Then if you detect it by photo detector, what you will see is essentially the same waveform, okay, with some changes, minor changes, but that is okay. Okay. So, this is the photo detector, and this mechanism of which you are modulating intensity and then detecting directly is called as IMDD transmission system, and IMDD transmission system, as I said, is quite popular and it is widely used for 10 to 40 Gbps optical communication system. You have to notice something else. There was absolutely no mention of the phase. So, as long as I am able to determine the bit boundaries, which is known as the synchronization problem, I do not have to know what is the optical phase here. In fact, my detection method is insensitive to optical phase. So, this is the direct detection which is completely insensitive to optical phase. Now, let us look at a different mechanism or a different receiver topology, which is called as delay line detection or delay line detector. What does this delay line detector do? Now, I take the signal which I want to detect, optical signal. Okay. So, this would be the optical signal that I want to detect, E of t, which can be written as square root Ps e power j omega st plus theta s of t, where theta s would correspond to the modulation that I have done. Okay. This is the phase which I have modulated. So, this signal is input to this device called as delay line interferometer, or rather delay line detector or delay line interferometric detector. Okay. What does this do? You first split your signal into two parts, okay, and then delay one part by a symbol time Ts. This of course assumes that I know where the symbol time begins and ends, that is I know where the clock information is, but that is something that can be easily extracted, okay, or it can be generated rather easily. So, if I have been able to do that, then what I do is I take the signal, split into two portions, then delay one portion and then combine them at the output stage. Okay. This particular device which is splitting a signal is called as a splitter or a combiner, because this is a two-way device. So, you take the signal from the left hand, then it will split the signal into two equal parts. Here we are assuming equal parts. You can actually split them in any ratio you want. You want to split the top part to contain 90% energy, bottom to contain 10% energy, you are welcome to do so. Okay. So, in this case, because we are splitting equally, and this splitting is actually power splitting. So, we say this as 50-50 coupler. Okay. Power being split into half. So, if you start with a power Ps, the power in this waveform, in this arm is Ps by 2, power in this arm is Ps by 2. This half corresponds to 3 dB, right. So, if you look at the power to power ratio here, this is ratio is half here, upper arm to input, that half corresponds to loss in terms of 3 dB. So, this is called as a 3 dB coupler, a splitter, combiner, 50-50 coupler or equivalent to a 3 dB coupler. Similarly, on the other side, what do I have? I have a combiner, right. So, I have again a combiner which will combine in the same ratio. So, I have a combiner which is combining in the same ratio in order to generate the output signal, which let us call it as E out of t. So, this E of t or E in of t is given by this expression, and this is what we want to find out, what is E out of t. To do that, I need to know in terms of electric field what happens to the signal as they get split here. Okay. As they get split, there will be a phase. You can actually construct a splitter in such a way that there is a relative phase between these two, or there is no relative phase. Okay. A general splitter will consist of two ports, okay, and output also consists of two ports. So, in this particular example, you can think of the other port being contributing nothing, it is a 0. Similarly, this other port has been neglected. Okay. So, what is this? So, if you call this as E1, call this as E2, then E3 and E4, this E3 and E4, which are the signals at this output, can be written as 1 by root 2, 1, j, j and 1. This j stands for a 90-degree phase difference, okay, times E1, E2. Simply saying that optical signal E3 at this port is given by 1 by root 2 times the input signal E1 plus j 1 by root 2 times E2. This j indicates that there is a phase difference. So, the component of E2 that goes to E3 will suffer a 90-degree phase difference, whereas the component of E1 which goes to E3 will suffer no phase difference between compared to this one. Okay. So, that is the meaning of having a j. You can construct in a very different manner in which the phase difference can be maintained as 180 degrees. Okay. So, let us take this 1j j1 as our example and then continue to proceed further. So, here if you look at this delay line interferometer, clearly there is signal in only one arm. So, let us say that is E1 arm, there is no signal in the E2 arm. So, E2 will be equal to 0. So, what would be the split values here? So, if I call this as E3 and E4, what would be E3 and E4? E3 will be square root of Ps by 2. It would actually be 1 by root 2, but I have taken the 2 inside the root. So, it would be square root of Ps by 2 e to the power j omega st plus theta s of t, whereas E4 which is coming because of E1 will be given by square root of Ps by 2, there is a j here, e to the power j omega st plus theta s of t, which can be written as square root of Ps by 2 e to the power j omega st plus theta s of t plus pi by 2. So, transposing or transferring this j multiple into exponential allows me to rewrite them in this fashion. So, you can see that these two signals are 90-degree out of phase. Okay. Now, you delay E4 by one time period. So, if you delay this one by one time period, what you get is square root of Ps by 2, there is no change in the amplitude, or we are going to assume that the amplitude is not changing so much. There is a change here, in place of t you write t minus Ts plus theta s of t minus Ts plus there is a pi by 2 factor, right. So, this omega s t minus Ts, and if you expand it out you are going to get omega st and omega s Ts, right. That particular term omega s into Ts, as long as you know what is omega s and you know what is Ts, it is simply a constant. Eventually that will go away, but at this point let us not make it 0. So, this is E4 that you are getting at this point. So, this is your E4 after delaying by 1 unit. E3 has not suffered any delay. So, E3 comes in directly as it is. Now, you have to combine. To combine them, you simply have to invert this particular matrix, right. So, this matrix represents the splitter matrix with E1 and E2 as inputs and E3 and E4 as outputs. Now, with E3 and E4 as inputs, what would be E1? So, you have to invert this matrix. I leave this inversion as an exercise to you. What I will assume here is that E3 will join E out as it is, whereas E4 will undergo another 90-degree phase difference. Okay. You can verify that. I am not going to do that one, I will leave that as an exercise. So, if you multiply E4 by another factor of j and then divide by root 2. So, multiplying by j is equivalent of increasing the phase by pi by 2. So, in place of pi by 2 I can remove this pi by 2 and write it as pi. Okay. So, please note that this would actually be different. So, I can write this as pi, but e to the power j pi is nothing but minus, right, minus 1. So, I can remove that also and then write down this as minus, and then because there is 1 by root 2 down there, right, I am adding them by 1 by root 2, there would be 1 by root 2 as well. What would be for E3? E3 would be 1 by root 2 Ps by 2 under root e to the power j omega st plus theta s of t, correct. Now, when you take these two signals and sum this would be the output signal that you are going to get. So, E out of t is given by 1 by root 2 Ps by 2 under root e to the power j omega st is constant. So, I can pull that one out, and what I get is e power j theta s of t minus e to the power j theta s of t minus t, which is the phase difference 1 unit earlier, t minus Ts, 1 symbol period earlier, this constant value omega s into Ts, I can choose this, right, I can choose this to be some multiple of 2 pi, some integer multiple of 2 pi, so I can remove that from the consideration. So this would be the electric field that I am going to get. Now what I do is, I take this output electric field and then put a photo detector here, so that what I get is magnitude square and a average of this, okay. Leaving the average part for you guys to work out, what I get here is half into Ps by 2, which is basically Ps by 4, and then this e power j omega st magnitude square will go away. So what you have to do is, first write down e to the power j theta s of t, and then take this theta s of t minus Ts as a common factor and pull it out, okay. So if I pull that one out, so what I get is e to the power j theta s of t minus Ts. This is the phase one previous instant, so I am taking that out. So if I take that out, I get e power j theta s of t minus theta s of t minus Ts minus 1, correct. Now what I do is, I take this fellow half of this out. So I get e power j theta s of t minus Ts and e power j theta s of t minus theta s of t minus Ts by 2 out. So if I take this half out, this first term will have a half with a phase difference, the second term will have e to the power minus j phase difference by 2, right. So if I call this theta s of t minus theta s of t minus Ts as delta theta s of t, which is the phase difference evaluated now, okay. So if I look at this phase difference, what I get here is e to the power j delta theta s of t by 2 minus e to the power minus j delta theta s of t by 2, right, and then take the magnitude square. So I know that this is e power jx minus e power minus jx type of a situation, right, taking this nothing but 2 sin x, so then squaring up will give me sin square x. So I get Ps by 4 sin square of delta theta s of t by 2. When the phase difference is equal to 0, I get 0. When the phase difference is equal to pi, I get pi by 2, sin square of pi by 2, which is maximum, and I get a power of Ps by 4. If you are not happy with sin square, do not worry. Instead of taking this omega s into Ts as n into 2 pi, you can simply take this as some 2n plus 1 into pi by 2. So that will add, in place of sin, it will convert that sin into cos, okay. So you get Ps by 4 cos square of delta theta s of t by 2. So you can simply adjust the operating point of this interferometer in order to reflect whether the phase difference of 0 should give you maximum or whether the phase difference of 0 should give you minimum. So this is the preferred one, so I can go to the preferred this one, and then this would be the photo current that I am going to obtain. What you have to observe is that this photo current is a function of cos square or sin square, does not really matter. In fact, one arm will give you cos square, the other arm will give you sin square at the output, but what is important is this is function of the phase difference between present and the previous slot. So if the present slot is 0, the previous slot is pi, you get the phase difference of minus pi, and then cos square of minus pi by 2, but cos square of minus pi by 2 is nothing but 0, okay. So this way you can actually extract, if the output is 0, then you know that the present and the previous symbols are not having the same phase, they are having different phases. So you can use this to decode dBPSK. If the phase differences can go to pi by 2, right, then there will be change in the amplitude level, right. So if the phase differences can be 0, pi by 2 or pi or 3 pi by 2, then the amplitude, corresponding amplitudes would be say maximum. So you get a maximum for pi and 0, and you get for pi by 2 you get cos square of pi by 4, which is half. So your signal level goes through minima, half and a maxima. So looking at these three outputs, you will be able to tell us whether the phase difference between this slot and the previous slot was equal to pi, or it was equal to pi by 2 or 3 pi by 2, both are the same, and it was equal to 0, okay. So by looking at the output, whether it is minima, halfway mark or the maxima, you will be able to tell us what is the phase difference delta phi s of t, and you can use this to demodulate differentially encoded QPSK signal or the DQPSK signal. We will stop at this point. There is one final detector that we need to talk about, which is called as coherent detection. Okay. The importance of coherent detection has grown so much over the recent years that the present generation and the next generation optical networks are using coherent detection. The primary difference between coherent detection and this other detection, the first one was direct detection, which did not use any information about the phase. The second one was differential detection. It was based on the idea that you have a phase reference, but this phase reference is not coming in from the actual carrier, but it is coming from the present symbol or rather the previous symbol. So, you are looking at the difference in the phases and then converting the difference in the phase into an intensity. So, the phase reference was the previous symbol, that is theta s of t minus Ts. This coherent detection is completely different. Okay. This detection mechanism actually starts with a local oscillator whose frequency is related to the signal frequency and whose phase is locked to the carrier frequency. Remember, carrier can be about 1000 kilometers away, and then you somehow have to have a local oscillator whose phase is in some definite phase relationship. You have to track the carrier phase, be in a certain phase relationship. This problem is not as trivial as I am telling you. It is a very, very complex problem, and previously the coherent detection mechanisms did not have a good interest because this phase lock loops which are used to track the carrier phase was very difficult to implement with optical means. Today you do that implementation in digital signal processing domain. Therefore, this coherent detection combined with DSP has taken over the transmission techniques in optical communication systems. So, all present and the next generation optical communication systems are using or will use coherent detection and corresponding digital signal processing. So, we will start with coherent detection in the next module, and then we will come back and jump back to transmitter physics. Thank you.